Okay, hang on. Okay, it's recording now, so let's go. You know when you go to a surface, you get those tents, low tents, and then you got in those tents, you've got these little poles to keep up the tents. Yeah. Let's say you've got this pole here where it's 6 meters tall. 10 meters away, you've got another pole that is 8 meters tall. Okay, 8 meters.
Okay.
6 meters. And you have to support those poles with a rope. So you can have a rope looking like this, or you can have a rope where it's like this, where you pin it to the ground. And you see you can pin it to the ground here and here, right? Do you understand the situation? So where should I pin it so that I would minimize the length of rope? So so I can have this purple length here. So where should I pin it so that I will minimize the amount of rope that I will need, Chelsea, for those two poles? They're 10 meters apart. So my first question to you is, how would you simulate this in Desmos? So that what is it that you're trying to minimize?
The amount of rope to hold the two poles up.
So you're actually trying to minimize this whole length here. You see that? So you want to set up a variable where you can scan through the whole scenario. Let's call this location at A. So you can slide A back and forth. And then as you slide A back and forth, suppose A is here, then you've got this red rope here. You see that? Chelsea? So so how would you set this up in Desmos? How would you simulate it? So load up Desmos. How would you set it up so that I can slide A back and forth between 0 and 10, because the two poles are 10 meters apart. And then as we do it, we can work out the length of the rope. So do it like this, Chelsea. Wait there, Chelsea. Let's imagine this is Desmos here. So this is your origin, 0, 0. You can set it up so that this is 6, and then this is this is 10 across, and then 8 up. So the coordinates here would be 10, 8. Right, Chelsea?
Okay.
Coordinates. Okay, yeah, set it up so that you can slide A back and forth. How would you do it? So set up our two poles first. So bracket. No, wait. Bracket first. Bracket. Set up our 2 points. 0, 0, 6, 0, 6, close bracket, comma, open bracket, 10, 8. So those 2 points represent our 2 poles. Scroll to the right on Desmos. Scroll to the right. Scroll to the right on Desmos. Oh, you can't see the second point. Now you can. Okay. So now you want to set up our slider A. Set up our slider A. Just type in A. Hopefully Desmos will recognize it. All right. No, it doesn't. Type in 2A. Yep. And then get rid of that 2. Oh, okay. Fair enough. We want to slide. What's our domain? What's the domain for our situation?
It cannot be a negative.
Yeah. So I can make A to be 1 million. Can I?
It could not be longer than longer than 10.
Yeah, so it's between 0 and 10. Yeah?
Yeah.
Okay, so go back to Desmos. Select our point. Put in another point, Chelsea. Put in another point. Go to the top input, the first box, and right at the end, put another comma in there, and then open bracket. I want to add another point. It will have a height of 0 and it's A across. So A comma 0, A comma 0. Close bracket. So now slide A back and forth. So why is it going into the negative realm? Yeah, from 0 to 10. Yeah, there. So as we slide it back and forth, I want you to draw the rope. Well, how would you simulate the rope in Desmos? What now? Yeah, you got to draw those ropes in there. How do you do it in Desmos? Your starting point would be what, six across, 0 across, 6. What? Why 6 across?
What?
Is that 6 or 0? I can't see.
0.
0, 0. Oh, you're joining it from the origin, right? To where?
Wait. No.
Yeah, 0, 6. Yeah. Join it to A. Test it. Slide it back and forth, Charles, just to make sure it works. Yeah, looking good. Now, what's going on now? Slide it back and forth. What's going on? Yeah, you want to join it to that tall pole. How do you do it? Well, how come you're leaving a gap in the third row? But it's the second pole is not really at a location of A, is it? No, I'm talking about the second pole. No, that's correct. The second point is correct. I'm talking about the pole itself, the top of the second pole.
What?
The top of the pole is not location of the pole, the tall pole. How many across? 0 across. Yes, 10 across. Yeah, there. Can you see that? Okay. Right, what are you doing now?
The second one and the third one.
No. That's just me illustrating it. So you don't need that. You can just slide A and A about to represent all 3 scenarios. Can you see that? Now the hard
Okay.
part. For any given A, you can work out the length of the rope. Okay, Chelsea?
Okay.
Now the hard part. So jump back to I drew. So for any given A, so at the moment, yeah, jump back to I drew. So let's try and use some simple numbers to try and understand what's going on. Let's say we are 2 across. So A is currently 2 meters. Okay, Chelsea, can you see that?
Mm-hmm.
Poles is currently at 2. Then what's the length of the rope? How do you do this? So what? So the length of the rope is really this blue length plus this long blue diagonal length. That's the length of the rope. Okay. But suppose
Okay.
you're at 2. How do you work out this length? How do you work out that length there, Chelsea? You're 2 meters away from the short pole.
Did you say?
How do you work out this
No,
this
after
green line?
that.
If you're 2 meters away from the small pole, can you see that green line? That's 2 meters away. How do you work out the
12.
y
No.
12?
You do Pythagoras.
Yeah.
Pythagorean.
So it's like me asking you to work out the length of the hypotenuse when this is 6 and this is 2, and it's a right angle triangle. Can you see that? So look at x. Yeah. Okay. I take your word for it, but it's not really 2 though, is it? It's that a. It's the distance of a, of course. Don't forget a is, we're going to slide a back and forth. So work out the length x. Do you understand this one, Timothy? Yeah. So no matter where a is, the diagonal length would be root 36 plus a squared. Okay, Chelsea.
Okay.
Okay. Now what about the green length here, Chelsea? What's that length? What's that length?
Mm,
You need to work out this length here. Let's call it x. We'll somehow work out x.
oh.
And don't forget, this distance here is 10 meters. So how do you work out that diagonal length, Chelsea? This length here. Cool. Okay, good. And then you square root it. Yeah. So it would be this thing here. Square root. Oh, wait there. What did you do? Hang on. Oh, wait there. How do you square this, Chelsea? Multiply this out for me. It's not 100 take away a square, by the way, Chelsea. Because you got to do like this. It would be 10 times 10, 10 times negative a, and then negative a times 10, and then negative a times negative a. Right, Chelsea? If you were to multiply this
Okay,
up,
okay.
but Chelsea, don't bother multiply that, Chelsea. Just leave it as it is. We don't need to do it because we're after the length, and the length is really the square root of the whole thing. Is that okay? So
Okay.
we can just leave that. So it would be 64 plus 10 minus a squared. Okay.
Okay.
Anyway, what's the so we need a formula for the length. What's the length of the rope for any given A? What's the length, Chelsea, for any given A? And we want to minimize that length.
What?
Well, for a location of A, what's the length of the rope? So if we're currently at A, what's the length of the rope? Yeah. Yeah, so now you can punch this into Desmos, and then for any given A, it will tell you the length of the rope. So to jump back to Desi, yeah, jump back to Desi and punch in the length, root 36 plus A squared. So no matter what location your A is at, it will tell you the length of the rope. And then later on scan it and guess where the rope will be at its shortest. Oh, actually, because you're under that square root already, you don't need the brackets, Chelsea.
No, I have to because it keeps
Oh, now
messing
you
up.
can. Oh, okay. Now you can delete it. I think now because you've already
Just let
got
it
that.
be.
Okay, fair enough. All right, come on now. 64 plus 10 minus A close bracket squared. Oh, brackets. Yeah, close it off, square it. Yeah, so now we can search for the what are we trying to find the biggest or the lowest?
The lowest.
Yeah, because we're trying to minimize the length of rope. So where is it roughly? So this is just guesswork now, Chelsea. But don't forget, it could be a weird decimal. We need to calculate it by using calculus later on. Where is it roughly? Yeah, so we don't know precisely where. We just know it's somewhere around there. Okay, Chelsea.
Yeah.
So let's next input, Chelsea. So hang on, jump back to I drew. Now that we've got a formula for the length, if we draw a graph of length versus our current our location x, Josie, scroll down a bit. I think when you sketch this in Desmos, it will give you a graph looking like this. Can you see that?
Yeah.
Because you're trying to minimize the length, you're actually looking for this lowest point. Well, at the lowest point, the gradient would be zero. So later on, we need to find d capital L over dx, and then find out when the gradient will be zero. Can you see that?
Mhm.
So if you draw this graph in Desmos, so jump back to Desmos and draw the graph L versus x. So I'll show you what I mean later. Go on, jump back to so new input. Okay, so now draw the graph. Let me think. Y equals. Remember, the y-axis will represent our length. So y equals. Yeah, y equals. So y represents a length. You've got to imagine the y-axis represents a length of our rope. So now square root 36 plus x squared. 36 plus x squared. Yeah, and then get out of that square root, and then plus square root 64 plus plus bracket 10 minus x close bracket squared. Yeah, and then zoom out. So you notice that your A location is actually pointing at the lowest point. Can you see that, Chelsea?
Okay.
Yeah, so we want to find that lowest point. So how do we find the lowest point? So jump back to iDrew. Jump back to iDrew, Chelsea. We want to find this point here. How do we find this point? How do we calculate it? Because by using decimals, you can only guess. You don't know precisely. I want to find this location. What do I do? Because I'm trying to minimize the length of the rope. What do I do to find the lowest point? Do you know?
Set it to 0. Set dy dx to 0.
Yeah, but don't forget, in our scenario is L and X. Can you see that?
Okay.
So earlier we had this formula here, Chelsea, where L equals square root 36 plus x squared plus square root 64 plus 10 minus x squared. Can you see that?
Okay.
This was the formula for our length, depending on where we want to pin the peg, right?
Okay.
If you want to find the lowest point, what do we do, Chelsea? What do we do to find the lowest point? I want to find the lowest point there. What's our next
Set
step?
x to 0.
Set x to 0. That means you're going to set x equals 0 right there.
I mean, set
What do we
L
do?
to 0.
Sorry?
Set
Set
L
x.
to 0.
So you're saying let the length of the rope be 0 length. What does that mean? So I'm not allowed to have a rope.
No,
So that's how do I find this lowest point too? Well, at the moment we've got a graph of L versus X. How do you find the lowest point of something?
what?
It's not me giving you this, Chelsea. It's not me giving you this graph. Let's say this graph here, y equals x squared. How do you find the lowest point? Chelsea. Chelsea, remember this thing you did? You find dy by dx. Look at the gradient.
Find dy by dx again?
What? What do you mean again? We've not done it here. That's just the length of the rope. That's not dy by dx, Chelsea. That's like me saying y equals something. It's the actual graph itself. What do you mean by find dy by dx again? When do we ever differentiate it? So this is the length of the rope itself. But wait, Chelsea, this is not a graph of y versus x. It's a graph of L versus x because this is our L, the length of the rope.
Okay.
So it should be dl by dx. Yeah. So let me just tidy this up. dl by dx. So differentiate this. So how do you do this? So you've got to imagine this as being 36 plus x squared to the power of a half, because that's what square root is, right? And then you've got to use a chain rule. So the half comes down, the bubble stays the same, the power gets minus by 1, and then you times the derivative of the bubble itself. Oh, the power gets minus by 1, Chelsea. Power gets minus by 1. Yeah. And then times the derivative of the bubble itself. What's the derivative of this? What's the derivative of that, Chelsea?
I'm thinking.
Cool. Okay. Plus, now this one's really complicated, Chelsea. Right, this one's complicated. You've got to visualize it like this. 64 plus the bubble squared, all to the power of a half. So be careful here. This is going to be a nightmare. All right. So the half comes down. The whole bubble stays the same. Well, wait, Chelsea. I know I'm just being picky here. Later on, that's going to give us a headache because it's so messy. We can't see anything. Wait. Let's do it again. We've got to.
Oh my god.
Because I know this is going to be complicated. I've done it before. Yeah. Keep it neat and tidy because it's going to get messy. Yeah. The power of net. Yeah. And then, wait. Why is that squared brackets? That means there should be a squared bracket somewhere over here. Yeah. Okay. Now you've got to times the derivative of the bubble itself, Chelsea. Here. Times the derivative of the bubble itself. So what is the derivative of this blue block? That 64 is just a constant. So really, your eye should just zoom into this bit here only. So the 2 comes down, Chelsea. The bubble stays intact. Yeah. The power gets minus by 1, but luckily it's 1. When you get 2, take away 1. Now times the derivative of the bubble itself, which will be what? Negative 1, Chelsea. That's a negative x there. Yeah. In brackets. Well, brackets, so it looks neater. Yeah. Can you see that, Chelsea? That's how you differentiate that whole thing. It is ugly. We've got to tidy this up. But now, Chelsea, this is easy to tidy up. This bit here. How do you tidy this up? Your eyes should zoom into this negative to the power of half. That's like 1 over square root of something. And then you times your half. So tidy this up. You understand? Your job is just to tidy this up for the time being. And don't forget, this gets multiplied to the top. Well, anyway, can you tidy up this massive long bit here? Yeah. And see, and you got a bubble over here, 2x. Multiply this to the top. Yeah. And then what else can you do, Chelsea? To the power of half is really the square root. And what about this 2 and this 2? They cancel each other out. Okay, that looks much better. Okay, cool. So this ugly thing here becomes this. Now, wait, Chelsea, this is going to be a nightmare to tidy up. Before we do that, let's tidy this bit up, Chelsea. What does this become? When you times minus 1, can we just do minus 2? Chelsea?
What?
Tidy up this thing here. What does this become?
-2.
Yeah, and then what about the 10 minus x? Look, Chelsea, wait there. I want to show you a trick. Wait there, Chelsea. You've got a block of 2 and a block of 10 minus x, right? And then you've got it times -1, right?
Okay.
Let's merge these two together so it becomes x minus 10, like that. Is that okay? Yay or nay?
Okay.
Yay or nay?
Okay.
Yeah? And then that becomes 2x and -20. Is that okay?
Okay.
So this thing here, this thing here really becomes whether let's let me tidy this in. So this becomes 2x minus 20. Is that okay?
Okay.
Right. So just remember that this block here is 2x minus 20. So now tie up this whole thing here. What does that become? Remember, your eyes should zoom into this to the power of negative of half. So that's like 1/2 square root of something. Yeah. Yeah. Well, rather than to the power of half, we use a square root. And remember, the 2 is outside of that square root. Yeah. Okay. Wait, Chelsea. What about this block? Yeah. Remember that block was this. Oh, wait there, Chelsea. Earlier, I asked you to multiply it out, but because I can see there's a 2 over here, I'm going to factor out the 2. So it was like this. Is that okay?
Okay.
Yeah, but don't forget, you've got to put this to the top. Where did this 2 come from anyway?
Because if you multiply it, that would be 2x minus 20. And then
Yeah,
20
but then
cancel out and the x cancels out. So it's 2.
what's this cancelling out thing?
Not cancel out, but if you differentiate it.
No, because you're differentiating it. No, you're not differentiating it again, Chelsea. Why would you differentiate it again?
Guess not.
Yeah, that's what it should be. Now what? Can you see the 2 2s? They would cancel each other out. Okay, yeah. So actually, I've shown you this about you know earlier I merged the -1 to give you this. I know it's a bit silly because I've just noticed this plus here. Let's factor this out. Let's factor out the -1. So this bit here is actually -1 and then 10 minus x. I want to just change it back to here before. Is that okay, Chelsea? You
Okay.
understand? Yeah. So this, Chelsea, if you rewrite this block as this thing here, you see y later. I want this to be a minus later on. You see y later on. Can you change this block, Chelsea, accordingly? You understand? Yeah, change it to -1 bracket. And yeah, you don't actually need that -1, but okay, fair enough. Okay, so now, Chelsea, drag that -1 out here so it overtakes the plus, so it becomes minus.
What?
Then you got
Can
one
you repeat
fraction.
it?
You know you got one fraction plus another fraction here. drag this one out here. So you've got one fraction, take away another fraction. You understand? Drag that negative one out. Oh, can I just, wait, can I just change it up here, Chelsea? Yeah, so stick a name, yeah. So now this is d capital L over dx equals this. So now what do we do? So currently we are at this important stage here. What's our next step? We want to find the lowest point right here. Oh, zoom out so you can see the graph, Chelsea. We want to find the lowest point here. Okay.
Okay.
Well, at the lowest point, dl by dx equals what?
X.
At the lowest point, the gradient will be 0, Chelsea. So we've got to put 0 into the gradient. Can you see that? Yeah. So set the whole thing to be 0, and then work backwards to find a value of x where the gradient will be 0, because that would then tell us this point, which we're trying to seek. Keep it neat and tidy, otherwise we're going to make some silly mistakes. Okay. So now, Chelsea, how do we find x such that the gradient will be 0? You see, you've got one fraction, take away another fraction. Luckily, this is the negative. We were trying to get it to be negative early on. So add this second block to both sides. So move this across. Do you get it, Chelsea? Try to keep it tidy, otherwise we're going to make some silly mistakes. Okay. Yeah. So now, Chelsea, you've got two layers here. 1, 2, 1, 2. Get everything onto one layer so that it's easier to manipulate. So what we're going to do is times both sides by this thing here. What does that then give us? Basically, it gets moved up to here, right? Yeah. Yeah. Keep it nice and tidy. Okay. So now times both sides by the denominator. Can I just do this, Chelsea, and move it across? Is that okay?
Okay.
Are you okay with that?
Mm-hmm.
Let me just move this down so it looks nicer. Okay. So now what, Chelsea? You see that square root thing? You can imagine this as being like one block multiply another block, and then you've got one block multiply another block. Okay?
Okay.
Whenever you have a square root, if you square both sides, it becomes neater. So when you square this, it's really at the moment you've got one block. Chelsea. At the moment you've got one block timesing another block, right, Chelsea, on the left hand side.
Mm-hmm.
When when you square it, it really becomes another block times another block. So you can merge these two together, you can merge these two together. Yay or nay?
Okay.
So hang on, just square both sides. What will you have, Chelsea? Square both sides. Bearing in mind that this is one block times another block. Yeah, so when you square it, it becomes that. No. What happened here? Yeah. And well, wait, Chelsea, it's not right, whether, because you've got this plus here, when people read your work, they will think that this is like one block. It should be this. Pyong, pyong. Can you see that, Chelsea?
Okay.
Yeah. Now it becomes a lot cleaner. Yeah. Oh, why is there a plus there, Chelsea? Why is there a plus there? Because when you square that, yeah, that looks right. Okay. Yeah. So now, it's going to get messy. We just got to live with it. Um, let me think. Multiply this out. So it's going to be 36. I think you're going to need more space than that, Joseph. Well, hang on. Well, just multiply that out. Yeah. And what about negative x times negative x, Joseph? Hey, how do you get 2x? Because 10 minus x times 10 minus x, when you get this times this, what does that give you? Yeah. Okay. So now the right hand side. Oh, thanks for wasting my ink. You've not done anything here. It's exactly the same. Multiply this out, Chelsea. You see that, Chelsea? Chelsea? Multiply this out. What's going on?
And
Oh, okay.
multiply it out.
Okay. I'll let you. Okay. Let me double check. Minus 20x plus x squared. Yep. And now Chelsea, multiply this out, multiply this, and then this thing here. We've got no choice but to do this a long way, Chelsea. This times this times this times this, and then this times this times this, and this times this. But because we're out of time, Chelsea, we're going to call it a day here, okay? But
Okay.
I know it's windy, but this becomes a lot simpler to work out as time goes on. I might send you a video for this if I can. If I make a video, I'll send it to you on how to solve this. Okay, Chelsea. But it's just
Okay.
a lot of the thing is this thing here will tidy itself up, and then it will be easy to solve. Okay, it looks
Okay.
messy. It does cancel out. Anyway, email me this video. Okay, Chelsea.
Okay.
Thanks, Uncle Chow, for the brilliant maths lesson.
Thank you.
Okay, see you next time. Okay, Chelsea.
Bye.
Bye bye. Remember to send it to me. Email it to me. Okay, Chelsea.
Mm-hmm.
Bye bye, Chelsea.